All right, so hello everyone. Welcome to the 11th lecture on open systems. And today, as you can see, we'll be finally talking about the master equation. But let me start with a spiel for you. So the way I presented it to you in this course, the theory of open systems, well, I presented it as something where we try to find a description for the dynamics of a system uh, induced by its interactions with the environment, right? So, like, when you look at it in this way, like your main goal, or our main goal, was to, derive from first principles, in a sense, the dynamical map, right, which quantifies this dynamics uh, uh, induced by interaction with environment. Uh, and what kind of effects this dynamical map, this dynamics has on states of the system, of the open system, was just, something you get what you get. But your main focus is to, derive the dynamical map from the physical principles underneath. So in this kind of approach to the theory, our main concerns were, basically achieving computability of the dynamical map while making sure that we keep it accurate, and at the same time trying to minimize the amount of information about environment that's needed to get this hopefully accurate description. And this is, it's manifested. It was manifested in the previous lecture, right, where we talked about this supercumulant expansion, probability, perturbation theories built around it. Everything was aimed to achieve computability, essentially, to figure out how accurate this given perturbation theory is. And, we talked about Gaussian approximation and stuff like that to make sure that we understand what kind of information about real environment is needed to achieve this whole description, right? So I would call this kind of approach, let's call it a first principles approach, okay? But this is not the only way to interpret the goals of the theory. The other way of looking at it is like this. You don't really care about the physics or the origin of the dynamical map. You just look at it as, let's say, some kind of abstract transformation that takes the state of your system and just transform it into something else, right? So you just, instead of focusing on origins of the map, you can focus on the effects the map has on the state, okay? And when this is the point of view you adopt, the framework you adopt, then your goal is not to, derive map from, real physical interactions between system and environment. You don't care about that. What you care about is to figuring out what kind of map, which you treat now as an abstract transformation, what kind of map you need to produce effects you desire, okay? To produce the effects on the state that you desire. And if this is the framework you adopt, then your main concern now is not computability, accuracy and stuff like that. Rather, it's like, okay, what are the fundamental constraints on my, design freedom of this abstract map? Okay, what can I put into this map that would still ensure that this map is viable, in the sense that it can actually be found somewhere in a real life, right? You don't need to like know exactly what kind of environment is needed to produce a given map. You just need the principle alone will be sufficient, right? What kind of shape of the map is allowed for it to at least be feasible to obtain with some kind of environment. Maybe you don't know exactly what kind of environment it is, but if you are sure that in principle it could exist somewhere in the universe, you are happy. So, so this kind of approach, when you don't care about the physics, you don't care about the derivation, you just care about this, you look at the map as an abstract transformation. Let's call it effects-oriented approach. Okay, so because we care about the effects maps have on states of the system, but not where it came from. And this is it's kind of useful to have this distinction in mind, know about this distinction, because it's when you study a literature, textbooks, or how people write or use open system theory, this effects-oriented approach is actually the most popular one. Okay, there are historic reasons for that, why this first principle approach is like less known, has lower rate of adoption, and I think we might touch upon those historic reasons at some point. But it's good to know, to be able to decipher why people are writing in this certain way about open systems, dynamical maps, and stuff. When you look at those writings from this perspective of this effects-oriented approach, it should be clear what's going on there. Okay. All right. So today I want to talk about this more popular effects-oriented approach. So, like I said, the main concern you have when you work in this kind of framework is, okay, what are those fundamental constraints on my that constrain my design freedom of those abstract transformations, abstract dynamical maps? So, like the industry standard for this, the industry standard answer for this problem is something that's called cross representation. So let me call it cross representation. It's something called cross representation, and let me go into detail what this means. So consider some dynamical map. So we take a dynamical map, goes from 0 to t. To dynamical map evaluated at some time t. Okay, so the definition, right? Partial trace e minus I t. There's Hamiltonian of system and environment, right? There is a bullet times initial state of the environment, right? We can express it as a partial trace. This is like the simplest definition, although we know now that you can also express it as a average over B trajectory. But let's keep it simple. And now let's do some algebra on this stuff, on this expression. So for one, we have here a initial state, which we can always decompose in the basis of its eigenstate. So use its spectral decomposition. Let's say the dimension is D. So we have eigenvalues, eigenkets. I will use psi as index because I used it previously when we talk about B trajectories. So let's use this kind of convention. So these are eigenvalues, which are positive. And these are just those guys form bases. Psi from 1 to D, or so normal basis, right? So if we put this guy here, and on the other hand, and on the other side, we can trace. What is trace? Trace of something is just sum over. You pick a basis. We can choose the same basis as eigenkets of the density matrix. So you can. I lost my cursor. Sorry. So 1 to D. psi prime, right? Trace is just taking the diagonal elements of the operator, right? So if we use those two representations of density matrix and trace, this our expression here will break down into the following double sum over our indices. I will write it like this: psi square root psi prime E minus IT H S E Hamiltonian psi bullet psi EI H S E T psi prime and rho E psi square root. So I just use the fact that the eigenvalues of density matrix are positive, so I can take square root of them. So rho E equals square root of rho E times square root of rho E. So we got here so we have here a super operator on the space of the system S, right? And it's now looks like this combination of like two symmetry looking operators on both sides. So let's call this guy here. Let's call this guy K psi prime, okay? And then if this is K psi prime, because this is, you know, E to of ITHSE, when you take matrix element using eigenkets in subspace E, you get, this is like a partial matrix element. So this, you don't get number, in return you get an operator, but now in space S only, right? So if this is an operator K psi prime, this guy here is then, you can see it, you can check it, that this is K psi prime dagger, okay? So in other words, we rewrote this dynamical map as like a sandwiching between operators K psi prime. Okay, and this is what's called Krauss representation. This kind of, you take a dynamical map and write it as this kind of sum over sandwiches, and the operators K. So they are called Krauss operators. Krauss operator. Okay, so Krauss representation then, Krauss rep is this set of operators K prime. Okay, so this is this whole set, and you can use them to construct the dynamical map using this formula here. And the thing that's the key property of this Krauss representation of those Krauss operators is the following condition, which they always satisfy. So you see, so this is like you take a sandwich K dagger and sum over, right? And now take a product psi prime dagger first times K psi prime, okay? So you take product like this, and you sum over all the indices, and using this definition, you can execute the calculation. There's nothing interesting about this calculation as far as I can see. So I will skip the step-by-step derivation. If you are interested in nitty-gritty, just check out the notes. But the thing that you will always obtain is that the sum gives you identity. Okay. So Krauss representation will be a set of operators K with some indices that satisfy this condition here. Okay. So this is the defining condition for Krauss operators. And now, things to note. There are a couple of things to note. For one, we obtain this particular representation, this particular K psi primes, because you noticed we picked a very special basis for calculating the trace as well as the expressing the spectral decomposition of the density matrix, right? Just picked eigenkets of the density matrix. And we got this set of operators. But you can always pick different bases. So for example, if I represent my trace, my partial trace, not using psi basis, but some, I don't know, mu. Okay, and this is some basis mu, which is not the same as basis made out of psis. 1 to D. Okay, I can always do that. Trace allows me to do that. And I can also pick a different decomposition of the density matrix, right? Rather than using the spectral decomposition, we psi. We learned it on like the first or second lecture that you can always decompose the density matrix, like this, psi k, where those are positive numbers greater than 0, and the set of kets psi k, this doesn't necessarily form a basis. This could be non-orthogonal kets. There are, for every density matrix, except for pure states, there are infinitely many ways to do this decomposition. So if we now take those two things and repeat the procedure for decomposing our dynamical map, we will arrive at an alternative Krauss representation. Mu k pk square root mu I minus I t h s e psi k bullet psi k e I t h s e mu pk square root, right? And this will be that would be a k mu k, and that would be k mu k dagger, right? So we will have a different Krauss rep made out of those new Ks, but it's easy to check again that they will nevertheless satisfy this condition that you take K dagger, multiply it with K, and sum over everything. This will always yield identity. In other words, for every dynamical map, there are infinitely many Krauss representations. Those Krauss representations are always connected to each other by this key property, okay? And now that would be some, let's say cute theorem, let's say, that you can write density matrix using this kind of sandwiching with those set of operators. But there is more powerful result related to this. There is something called Nymax. Nymax, that's the surname of a guy. Dilation theorem. This is a key result, which says that when you have a set of operators k indexed with some m that satisfy this Krauss condition, right? So someone just emailed you a set of operators, and this set of operators satisfies this condition. Then how do I phrase it? Then it is always possible. Then it is always possible to find an unitary operator. Let me write it as SZ, okay, in space SZ. So we have our system space S and some other subspace which we call Z, and there is and we can always find an unitary operator that operates in a composite space, okay. So we find this unitary and cat in space Z, some psi Z, okay, such that sum over M K M bullet K M dagger equals partial trace over Z U S Z bullet times psi Z psi Z S Z dagger. All right. So what this means, so if you know this, then formally you can treat this postulated subspace Z as an environment. Formally, it's indistinguishable from environment. This unitary operator here, you can think of it as a evolution operator in the total space evaluated at certain point in time, right? And then this cat here, this is just a initial density matrix for environment Z, okay? In other words, to sum it up, whenever you have a dynamical map that is a partial trace of real unitary evolution with initial density matrix in environment, you can represent it in many ways using Krauss representation, right? Using Krauss operators. You can construct it like that, but also the other way around works, that if you have a Krauss operator satisfying this, then in principle there exists environment and the Hamiltonian and the initial state that will, upon partial trace, produce you density matrix for dynamical map, sorry, that would be represented by this set of cross operators. So this is what I was talking about, this effects-oriented approach, right? You don't care about the physics, real environment that actually produces dynamical map. You just want to know what is the shape of transformation of density matrices that will ensure that in principle there exists some environment that would produce this kind of transformation upon partial trace. So this is Nymax dilation theorem is exactly that. This is what it says, that if you construct your dynamical maps using operators K that satisfy this condition, then you can be sure that at least in principle, somewhere in the universe, there could exist some environment that would produce this kind of dynamical map, right? You don't care about the details, what exactly is this environment. This is not what we are interested about. We just want to know that this is like physically viable design of an abstract dynamical map. Okay, so this is Krauss representation, and to give you some example how you work with this stuff. So let's say you have a qubit, and you want to have some you want to see what you can do with it. So you know that you have Krauss this Nymax dilation theorem. You have you can just pick some set of operators that will satisfy it, and you will have some viable dynamical map. So in case of qubits, all operators can be expressed as some combination of Pauli matrices. So there are not so many options to test, actually. And let's say, for example, let's take something like this. So let's say K1, that's equal to 1 plus some positive number P divided by 2. Let's take square root here, times 1 times identity. K2, we take 1 minus P divided by 2 square root times sigma z. And that's it. We take to postulate two Krauss operators. We have to check if they satisfy the condition, right? So we take K1 dagger K1 plus K2 dagger K2. Okay, we see. So the first one, K1 is easy, right? Because just identity. So we get 1 plus P divided by 2 times identity. The other guy will have 1 minus P divided by 2, square root goes away, and we have sigma z square, right? Because sigma z is Hermitian, so dagger does nothing to it. By square is equals 1. As identity. Square of Pauli operators is always identity. So what we get here is 1 times 1 plus P divided by 2 plus 1 minus P divided by 2, so equals 1. So the condition is met. This is a proper Krauss representation. And how it works, what effects it produces? Well, let's just check. Let's take some density matrix for our system, initial density matrix M. So M. And let's act on it. So if we have 1 plus p divided by 2 row 0s, this is the first guy, right? Identity does nothing. Plus 1 plus, not plus, sorry. Minus p divided by 2 sigma z row s0 z, the sandwiching with sigmas. And when you do your algebra, you will get that in the matrix of row after the transformation, in the basis of eigenkets of sigma z, so arrow up, arrow down, will look as follows. So the diagonal elements won't change. That's cool. Of diagonal elements, on the other hand, will change. What's what I'm doing? Sorry. Row 0s. They change because they will be multiplied by this parameter p. Row 0s. And also p. Okay. So this is how you do the effects-oriented approach. You want something that, let's say, does some decoherence on your qubit. Well, this, if p is smaller than 1, then this kind of set of Krauss operators will attenuate your of diagonal elements in the density matrix. And you can be assured, because of Maimach's theorem, that in principle there could exist environment that would produce this kind of dynamical map. Okay, so this is a Krauss representation. Now let's all right, so traditionally, so that was Krauss representation, very popular stuff and useful. But traditionally, when people talk about those viable abstract maps or maps with Krauss representations, they often call them, so maybe let me write it like viable. How do you write viable? 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 This is how you write it, viable. Yeah. Viable maps, and people call them, maybe you even heard this kind of name, as completely positive. Sometimes they add also and trace preserving maps. Shit. So you have density matrix transformations that have Krauss representation, or in other words, dynamical maps that are obtained by a partial trace of a unitary in system environment space that acts on given initial state in given initial environment state. People call them completely positive maps, okay? And as you can expect, there is some history behind this very specific naming convention, right? It's not just a shorthand for viable map. It's not even shorthand, it's the opposite. Oh, and completely positive is like CP, abbreviative, completely positive, CP for completely positive. So this idea of complete positivity, this is something that arose in I guess it's in 70s, as like a quintessential effects oriented concept. People were trying to like figure out those design constraints. They came naturally to this idea of complete positivity, which I will now I will try to introduce it, mimicking this historic approach. Okay, how people came to this this concept of complete positivity. So we have Kraft's representation. That's one, and now let's talk about ideas behind complete positivity, and then we will tie them together. So a story time now. So let's consider story time. Story time. Okay, so let's consider some system S, okay, which has its dynamics defined by dynamical map. Dynamical map, I will just think of it as an abstract map. So there is some map D S because it acts in system S, and there is some time, right? Because it generates dynamics in time. So what I mean by that, if I take any initial state in S and I act on it with this dynamical map D, I get rho TS, right? This is what I mean, that this D represents dynamical law in system S. Okay, and now if you look at this D from this effects-oriented perspective, so you willfully ignore all the the background of actual physical environment coupling with the system. You completely ignore that. Don't think about it. You just look at this abstract D, and now let's try to figure out what kind of properties this D has to have to be a proper representation of the dynamical law in system S. Okay, and like the lowest of IQ stakes would be, okay, if this is the very least, the smallest possible constraint this D has to satisfy, well, if we wanted to transform density matrix into density matrix, right? So at the very least, this D has to, make sure that the output is something that can be counted as density matrix. That is, this rho TS, it has to have trace one and be positive, right? So this leads us to the first conclusion, that there are like two things that we require from D at least. So thing one is D preserves, maybe not. D is trace preserving. So this is abverative is TP, trace preserving, which means that for every time greater than 0, trace DTS rho 0S equals trace of rho 0S, which equals 1, right? So that's one. So we had at least the output of action of this map will have trace one. That's good. But the other thing, DT is positive. Then you have P for positive, which means that if rho 0S is a positive semi-definite operator, then dt as rho is also positive semi-definite. Okay, so those two conditions, they are satisfied, right? We say that dst is PTP, so positive trace preserving, and this guarantees that whenever it acts on a density matrix, it will spit out something that also counts as density matrix. Okay, so this is all you need actually. These are all the constraints that are necessary to have a viable dynamical map. Well, they are not, as it turns out. And to see what is missing, we need to expand our horizon a little bit, right? So, so we are looking at system S. It has its dynamical law, but there are more systems, physical systems in the universe, right? So let's take one of them. So we have our S with its dynamical law d st, and let's take some system, other system. Take other system Z with its own dynamical law. dzt. Okay, and now let's assume that S and Z, at least starting from t equals 0 from the initial state, they are independent of each other. Okay, there's no interaction between those two guys. What happens before that? We don't have to specify it right now. So if S and Z are independent, then the dynamical law in SZ in the total space is so dSZT equals dST times dZT, right? Independent, so they evolve independently. There is no crosstalk between them, so the total evolution is just evolution in S times evolution in Z, right? And now, okay, so we constructed like a new dynamical map, all right? So well, we can assume that this guy is PTP and this guy is PTP because we want them to be dynamical laws. And now this DSZ, a composite evolution, well, system SZ is also a quantum system. So its evolution, this dynamical map also has to be we would expect it to be PTP as well. PTP, right? Question mark, right? If viable dynamics in a system is PTP, then if you construct this viable dynamics by taking two independent dynamics, you should get something that's also PTP, right? But the question mark here, right? Well, if everything is fine, everything is fine. Everything is fine if the initial state as Z is also a product state. So if we start from uncorrelated state of our two systems, then it's quite straightforward to check that this S0 times SZ, that the trace of this guy, right, it breaks down into trace in S times trace in Z independently, rho 0 Z, right? And since those two guys are PTP, we know that this equals to trace of rho S 0S times trace Z 0, which is the same as trace of the initial state, product state. So that's cool. Equally easy is to check that it also, the output also will be positive. ZT acting on rho S 0 times rho 0 Z, which is nothing else but S rho 0 S, right, times DZT Z 0. And it is positive because a outer product of positive operators is positive, right? So this, at least if we start with a product state, initial state, we preserve trace and we have positivity. So okay, this looks fine. It is still fine, even if we allow for classical correlations. That is, if we set the initial state as 0 as Z, something that is of this form, some pk rho 0 s k times rho z 0 k. So it's and pk's are positive, pk's are non-negative, and they sum up to 1. This kind of state is called sometimes separable state, and it's like models a classical correlations between two systems. If you take this as initial state, still you will have, when you act with this composite map, you will still preserve trace and you will preserve positivity as well. Everything is fine. The things break, the things start to fall apart, things break when the initial state is entangled. Well, definition of entanglement is basically that as Z0, it cannot be written as separable state. So it's not of this form. Then, as it turns out, if you act on entangled state with this composite map, ds times dz, sometimes the output sometimes won't be a positive operator, okay? And it's actually so unreliable, this positivity here, that there is something that's called a famous result, something that's called Perez-Horodecki criterion for entanglement. Where you use the fact that this composition of PTP maps preserves positivity and trace for classically correlated states, but not necessarily for entangled states. So the criteria is like set up in that you create this map as Z made out of identity. Identity is PTP, is positive trace preserving, and you multiply it with transposition. So it just takes, it's not identity, but it takes a density matrix and transposes it. It's also PTP. So this guy is PTP, and this guy identity is PTP as well, right? And this test, this criteria, it works like, okay, so you take you take some state as Z, right? And you think, is it entangled? This is your question. You ask this question. And you take this row as Z0, which you suspect of being entangled. You act with this composition of PTP maps, and you check if output is positive. If it is positive, you know for sure that no. If it's positive, you get unconclusive results in general. But if it's not positive, you are damn sure that it could not be classically correlated state. It had to be entangled. It's a if and only if, only for S and Z being qubit, 2 qubits or qubit and qubit. Okay, so the bottom line is that PTP, so positivity and trace preserving only, is so insufficient as a constraint for proper viable dynamical map that is actually, it's used as a criterion for detecting entanglement. We are using its failure to preserve, to work properly, to actually, to check some stuff as a witness of entanglement. So PTP, it's so insufficient that actually you can use this insufficiency to other means. All right. So our first guess, those two first points, turns out to not be enough. Okay, we found the failure point in this scenario where you take two maps and you act with them on entangled states, right? This was a failure point. Okay, so let's fix this. Let's fix this particular pain point. And this gives us a third requirement we will put on our map DS. So to fix the issue with entanglement, let us demand the additional condition. So we call it number 3, and it sounds kind of weird. It sounds kind of weird. So we say that DST is such that DSZ with index D T that equals our map DS, which the condition is 4 times identity. So a transformation constructed to act in a composite system SZD with d-dimensional subspace ZD, okay, comma. It sounds really weird, but we'll go over it. Is positive for any D and T greater than 0. Okay, so you take the test, I mean, the condition is for DS, all right? And you say DS has to be such that when you combine it with some other system of dimension D, and you create this transformation that has DST times identity in this other system, this combined transformation itself is also positive for any dimension, any time, and so forth. Okay. If DS satisfies this 1, 2, and 3, we call it completely positive. If DST satisfies 1, 2, and 3, we call it, so it's not only positive trace preserving, it's actually completely positive trace preserving. Call it completely positive. So CP, TP, you can, TP is always assumed here. Okay, so now this is very weird. This condition is very weird, right? But it does indeed fix the issue with this entanglement stuff. Because if we go back to our scenario of entanglement, so if you take ST time D ZT, and if we assume that this is CP and this is CP, okay, and you act on any state whatsoever, whatever the state it is, so you can just make it like this product. You can write it as identity in Z, composed with identity in S times DZT, okay, acting on the state. And now complete positivity means that this is positive, right? Because this condition is constructed in such a way that CP is when this is positive. And then you have this guy which also preserves positivity. So it acts as positive state, spits out positive state. So this will also be positive, okay? That's why this is formulated in this way. So while PTP didn't have this property that when you take an outer product of two PTP, you get PTP, but CP has this property. So you get CP, you combine it with other CP, you get total CP. So it's like consistent in this way. And it solves this blind spot with entanglement, all seems fine. And now, there are a couple things to know. This turns out to be sufficient. Those three conditions turn out to be sufficient to constrain all the viable dynamical maps, abstract dynamical maps. However, there are many incarnations of this condition 3. Okay, there are many equivalent mathematical conditions that gives you the same the same kind of maps. Okay, there's a whole plethora of different formulations. Usually, this number 3 it does something like this, that you take additional system, you bring an additional system, you construct some transformation, and they usually there is some reference to entangled states in those alternative definitions. There is a nice paper that like gives you a list of many of those kinds of definitions. Each has its own strengths and scenarios where it is useful. But from our perspective, there is one additional equivalent definition of complete positivity, which actually ties back to Krauss representation, because you see maps where there is something that's called choice Hoy's theorem. Again, Choi is a surname of a guy, and it says that maps with Krauss representation are CP. Okay, so complete positive. This is not nothing special, because every physical dynamical map, that the real dynamical maps, right, have Krauss representations, and you know, this complete positivity is supposed to characterize real maps. So if you have Krauss representation, this means that you are looking at least in principle, real dynamical map. So for sure, it has to be complete positive. But there is also other way. CP maps always have Krauss representations. It's actually one S, not two S's. So always have Krauss rep. Okay. So this ties everything back. Okay. So and every real map, dynamical map, any viable dynamical map has Krauss representation, and it's also CP. And every CP map has a Krauss representation, which means that every CP map is, in principle, there is a real environment that can produce it, right? So that's why we are allowed to say that you know, real dynamical maps are, you can say they are just CP maps. Okay, all this story with mathematical definitions, it has its uses, but the most useful thing about it, I think, from practical point of view, and especially from this effects-oriented point of view, is that the complete positivity is equivalent to Krauss representation. Because Krauss representation gives you some parametrization for your maps, that you know how to construct map from simple building blocks in such a way to make sure that it will produce something that's viable. Okay. So on this happy note, let's take a 10 minutes break. Okay, and then we will wrap this up with we'll wrap it up with master equation at the end. All right, let's carry on. So we're moving past CP. Next point, time-dependent Krauss representation. Okay, so here is the thing. If we recall that this, like, the first encounter with Krauss representations, like it's kind of like first principles blueprint for Krauss representation, right? So we took our dynamical map, right, and we decomposed it like this. We called this guy Krauss operator, right? This thing here, and you look at this, and this K psi prime, you know, this is like a snapshot of the dynamical map at a, you know, given point in time t, right? So we could add here that this actually depends on T, right? Because T is here. We start from first principles. We have our unitary dynamics underneath, right? So we can actually track the time here, right? So now, if we follow this this blueprint for every point in time, right? We can like construct the whole family of Krauss representations, right? So we could have like K psi prime of T. That's, we have our indices, but also there is the whole set for every point in time, right? So in that way, if we follow this blueprint, in the same manner for every point in time, you can now take the snapshot at each time and conjoin them together into one, one representation that represents not only dynamical map at each point in time, but also it has this, the flow of time is also encoded in it, right? So you take, if you have this this blueprint, you can construct it like this. Then you see that you have a cross representation for every point in time, and then even it's such that I guess how to write it, that it's like there's follows time. So if I take some psi prime at some time u, and I allow the time to pass from u to t, then I end up with psi prime of t. Something. I want to say that this is the the parameter t, tells us we know how to connect different representation taken as snapshots at different times. There's logic to it. It actually represents not only dynamical map at the given point in time, it represents dynamical map as a function of time as well. Okay, and we can achieve it because we have a real interaction with environment underneath, right? I'm underlining this because what about if you switch to this effects oriented approach, where you forget about the physical origin of stuff, right? How can you construct this kind of how can you conjoin snapshots at different times together? What is the rule that would allow you to construct something like this, right? Because you have some abstract transformations parameterized with a set of Krauss operators, but where is the logic that connects to those different representation in a temporal manner? Where is the temporal connection between them? And the truth is that if you don't have this first principle stuff underneath, there is no temporal connection. You have just set of Krauss operators, different set of Krauss operators. There's no purely logical reason why one should be treated as a representation at some time u and the other at some later time t. Okay, if you want to have this kind of temporal connection, well, that you have to introduce additional constraints of your Krauss representations to achieve something like this. Okay, just having this one condition just having this condition MKM dagger KM one, this doesn't give you any information about temporal relations between different representations. So you need something extra. And of course you can imagine like there's infinitely many types of constraints that you could try to introduce that would give you this kind of temporal connection. But there is one specific constraint that is known to lead to very useful parametrization. So additional introduce an additional constraint. So we have our family of Krauss representations of T, M, and T. It satisfies for every T. It satisfies the Krauss, the standard Krauss condition, right? So equals 1. And now the thing that we will introduce the temporal connections will be that we demand that the map represented by this family of Krauss representations satisfies the simplest form of composition rule. In other words, we will demand that you take M, K, M, T, bullet, K, M, dagger, T, and you compose it with M, sum over M, K, M, U, bullet, K, dagger, M, U. It will give you a map KM T plus U, bullet KM dagger T plus U, right? So we compose map at U with map at T, and the simplest composition rule would gives us just map at T plus U, sum 2 times. So we have a family that satisfies this, and we demand that it also satisfies this. Now, from back in the very beginning of our of this lecture, we learned that the composition rule is connected with dynamical equations, right? If you have if your map satisfies dynamical equation, Schrodinger equation, whatever, then it implies composition rule. And in particular, this simplest composition rule, where your map is just a one parameter semi-group, let's say, and the composition produces just map at the sum of parameters. This corresponds to the following dynamical equation. So this is mathematically equivalent to saying that when you take a derivative of a map, Km T bullet, K dagger M T, take derivative, then it has to give you something like this. L let me call this KKLS. So enigmatic index here, soon will be explained. KM T bullet dagger M T. And the initial condition is KM0 bullet KM0 dagger equals bullet. So demanding composition rule is the same as demanding that this map represented by this family of K satisfies this dynamical equation, where this super operator L here, constant generator. So it is constant, and it's a the superoperator is a generator in the sense that this dynamical equation can be solved quite easily, because this implies the solution that Km T bullet Km dagger T equals e to power TL GKLS. No time ordering is needed because the generator, for this composition rule to be true, this generator has to be constant. Therefore, the map represented by our Krauss operators with this additional constraint can be written in this form. So it's exponent generated by this L, superoperator L. And now, if we just look at this, so we just look just at the composition rule, this is all that we can extract from here about this generator L. Okay, we just know it has to be constant, nothing more. However, this has to be simultaneously combined with this Krauss condition. Okay, and when you take that your map has this form, L is constant, and also this has to be satisfied, well, then you can severely constrain the form of this generator L. How to show it? Well, there were 4 guys in 70s, Gorini, Kosakowski from Torun, and Sadershan, plus independently Lindblad. That's why we have GKLS in alphabetic order. So this is Gorini. This is Kosakowski. This is Lindblad. And this is Sadershan. So that so weird to write it like that. GKLS or GKLS in short. That's why this index here. So they took those 2 conditions, and they proven, like I say, GK and S together, L independently. They proven that to satisfy this Krauss condition, the generator has to be of what we will call GKLS form. GKLS form. That L GKLS has to be equal to minus I commutator of operator H plus sum over indices mu. There is a matrix here, G mu, times L operator index mu, bullet L mu, dagger, minus, god damn it, not enough room, 1/2 a anti-commutator superoperator here, and you anti-commute with L nu dagger times L mu. And again, anti-commutator L AB equals AB plus BA. Just for reference. And so this is the general form, and here you have H is an arbitrary Hermitian operator. Whatever it is, only need that it's Hermitian. 2 matrix G, so let me write it like this. So matrix made out of those coefficients G, mu, nu is positive semi-definite. Semi-definite. And L mu, this set of operators mu, arbitrary. Whatever you wish. No constraints here. Those L are sometimes called, or often called, jump operators. We won't go over the proof of GKLS form. In the notes, there are references to original papers, which are not the simplest to read, but there is also simplified versions of the proof. If you want to see it, go for it. We won't go over it here. We'll just bask in a glory of this result. So again, so Krauss representation is like a parametrization. If you want to construct a viable dynamical map, right? You have Krauss representation, which tells you, okay, you can take some kind of set of operators. There's one condition to satisfy, and if you do, then you have a like proper viable snapshot of dynamical map, right? But if you want to have a time in your dynamics, which you usually want to have something like this, then you have GKLS theorem, which tells you, oh, you want dynamics, at least this simple kind of dynamics that's generated by a constant generator. Well, you can take a bunch of operators, which are almost not constrained, any Hermitian operator and any set of operators, Hermitian, whatever, doesn't matter. And just the only thing you have to worry about is just this matrix of coefficients to be positive semi-definite. And you have a valid generator. That's pretty powerful. I mean, you can like build your own maps with building blocks that are pretty easy to understand. Okay, you can like see for yourself what this does to density matrices. Okay, so this is quite powerful result. It's often expressed in the form of dynamical equation for the density matrix, because you have rho Ts, right, which is equal to ETL GKLS rho 0 S, right? This is state. So you can write a dynamical equation for this rho T. If I calculate this derivative, I will get, this is pretty simple, right? It's H commuting with Ts plus this other non-Hermitian part. You will have L mu, L mu rho Ts L nu dagger minus 1/2 L nu dagger L nu anti-commutes with OS of T. Okay, and this is what's called master equation. Master equation. So this is the namesake, okay? It's basically GKLS form, but when applied to the state and you look at the dynamical equation for that. So this is the famous master equation. And I think it's no great exaggeration when I say that this theorem they proved, because it was Lindblad and Kosakowski with Gorynie, Sadeshan, this was actually in parallel. They work on it and find the answer at the same time. Okay, and the history, how they arrived at this theorem that gave them this Gekaless form. This is where discussions of complete positivity came in. This all harkens back, the Krauss representations, all this stuff. It harkens back to those times in 70s where they worked on mathematical problem of constraints on a viable dynamical maps. This is what they were looking for, and ultimately they arrived at this theorem that gives you this form, this parametrization, and the simplicity of this parametrization, the freedom of choosing the jump operators and everything else. This is what I think marks the beginning of the open system theory as a subfield on its own. Before people consider, of course, open systems, we would call them open systems, but it was like they had some techniques how to incorporate the influence of environment, but like specialized for their systems. Like some I don't know, electron gas in a solid state. They had their methods for dealing with some phonon excitation and stuff like that. In laser, quantum optics had their own methods. Each field has its own theoretical methods for dealing with environments. But once this like universal parametrizations came up, people started to think in abstract about open systems, because all of a sudden we don't have to go to first principles to derive what is the dynamics given this kind of interaction with this kind of environment. You can now just construct, postulate dynamics without worrying about physical background, which might be very complicated. So this open up whole field for this mathematical exploration, and also maybe also with some applications in physics, which actually brings us to the next point, which will probably end this part on 5.3, master equation as a physical model. So, like I said, if you are looking from this point of view of effects, abstract transformation, this is a pretty powerful result, right? Very nice. If you're a mathematician, you can go nuts with this, right? It's you will have topics to think about for sure, but immediately people also started to think, okay, but is this actually we know that in principle this represents some real environment. There could exist in universe a system where this kind of map, this GKLS map, is actually describing a real dynamics. Something like that could exist in principle. However, is it any good as a model of real systems that we actually might encounter in situations we want to consider, right? So basically, people try to figure out this connection between this effects-oriented abstract approach and the first principle approach. Can you show that when you go from first principles, you take real environments, that you actually will arrive at map that would be generated, but GKLS form will generate it? Is it real or is it completely fake, right? So here comes the question about connection between this abstract and first principle stuff. And the first result came from a guy called Davis. Where is it? Here it is. Davis, EB. It's also 70s, end of 70s, I guess, where he demonstrated that, where he gave a mathematical proof that when you take a dynamical map, so you just take a real dynamical map, something like this, okay, where you have a partial trace, and you have the if you allow me to remind you of some notation we used on previous lectures. So, right, so this dynamical mapping interaction picture, where you have a Hamiltonian SA that has HS part times 1 plus 1 HE, and there is an interaction, right, between two guys, and this was a shorthand for sum over alpha as alpha times F alpha. And F, if you remember, it's always shifted. There is a bare interaction, but we shift it by the average, and same goes for the Hamiltonian. Right, so this is just a reminder of what we used. And what Davis showed, that when you take this map, okay, you take this map and you take it to a very specific limit where coupling goes to 0, and times goes to infinity, but in such a way that lambda squared times t is constant. Okay, so the coupling becomes weaker and weaker, times goes to infinity, but there is a certain rate between them. And you go to infinity not too fast, and you go to 0 with coupling also, there's some combination with this. This is called weak coupling limit. Weak coupling limit. Then he showed that in this limit you get asymptotically map E KKLS, okay? And there is some coefficient here. I would like to, it's not time. I actually don't remember what exactly is what happens with time here. Because it's like, we go to t goes to infinity, lambda goes to 0, but there's this constant here. There is some coefficient, let's call it tau, whatever. It will represent something. But the point is that you actually arrive at map that is generated by a superoperator in GKLS form. And this GKLS form is actually quite specific because it's like connected to the initial Hamiltonian, right? So this is a asymptotic result. And immediately people ask, okay, but what if coupling is weak, but not infinitely weak, and time is actually some t, not some t goes to infinity? Will this GKLS form be a good approximation to the real map in the limit of weak coupling, not in the limit, in the regime of weak coupling? We know that in the weak coupling limit, you get there, but what about weak coupling regime when it's small but finite? Okay. And we will show on the next lecture that indeed you get there when you consider this weak coupling regime. We will deploy our methods we learned previously our perturbation theory, supercumulants, to show that actually there is a parameter regime where you can show that this GKLS model is actually reflects, it's a good approximation to the real dynamical map, which answers the question that yes, the result, the GKLS, the master equation theorem is a good model of reality, at least in, I mean, we can identify a regime where it is a good model. All right, so that would be that for now.